Hello, and welcome to this YouTube video on tempering of resistance welds. To begin with, let me start by sharing the screen so you can follow along on the PowerPoint. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting and training services business is on the web at welding-consultant.com. Today, we're going to talk about tempering of resistance welds. Resistance weld is one of the common welding processes, and I have already shared other YouTube videos on resistance welding. So if you go to the YouTube channel and click on the resistance welding playlist, there you will see introductory information on resistance welding. In resistance welding, we typically take two electrodes, and I'm showing that in a schematic form on the left, and trying to weld, say, two pieces of steel. And I'm showing the current flowing through the electrodes, through the part, and down through the other electrode and back to the transformer. The welding pulse, as I've shown in schematic on the right-hand side over here, where we have current on the vertical axis and time on the horizontal axis. So when we use resistance welding, we send a welding pulse. Now, the shape and size might be different, but if there is a situation where we need tempering, then we typically send a second pulse after the welding pulse, which is the tempering pulse. And the tempering pulse is used to reduce the hardness of the weld. And in the following slides, we're going to review how that whole process works. Now, one of the biggest concerns in welding is the fact that martensite, which is a very brittle phase, can form due to rapid cooling of carbon steels, and that can lead to a weld that is very brittle and have risk for crack growth. So we definitely don't want too brittle a weld. The amount of martensite that will form will depend on steel composition and carbon content. Here again, there are two videos on the TTT and CCT diagrams in the metallurgy playlist on how that happens for carbon steels and low alloy steels. It is possible to reduce the martensite by making changes before welding, such as, say, reducing the carbon content, reducing the alloy content, and in some situations, applying a preheat to the parts before welding. However, those options are not viable in some situations, and then you end up with a weld that is brittle, and now you have to reduce the hardness by tempering. As I mentioned before, there are other videos in the metallurgy playlist which will give you information about CCT and TTT diagrams that we are going to refer to in this video. Here I'm showing you a schematic of a TTT diagram where we have temperature on the vertical axis, time on the horizontal axis. And this dark line over here is the boundary where these phases will start to form. So for example, when you're cooling steel down towards room temperature, if you cool it down at a slower speed, slower rate, you're going to get a phase called perlite, which is a mixture of ferrite and cementite. If the cooling rate is a little bit faster, you might get bainite. If the cooling rate is very fast, you're going to get martensite. Now, martensite will be the hardest phase that can form in the weld. And we can measure the hardness of the weld by micro hardness testing on weld sections. So how much hardness would you anticipate in a weld? So we're going to look at this chart, which is hardness on the Rockwell scale on the vertical axis and carbon percent on the horizontal axis. The source of this chart is the Metallurgy Handbook. So let's say you're welding a steel which is 0.2% carbon. So you would anticipate the maximum hardness in the weld of the order of 50 HRC, which is quite hard. So here we're going to show an example of a weld. This is a resistance weld. It's a cross section. And you can see the heat affected zone over here. And you don't see any fusion zone because this is one of those welds where there is no fusion in the weld. And you can see more information on that on the video in the resistance welding playlist, which says types of bonds in resistance welding. So resistance welding is a process where there are situations where you may not form a fusion zone in the weld. So this weld was sent to the lab for a hardness scan, and starting from the top to the bottom, 1 to about 15 spots, and showing on the screen in the chart form on the right, you can see that the hardness in the heat affected zone, which seems to be the darker region over here, is now close to 50 or slightly above that. Whereas the base metal hardness is around 40 on one side and about, say, 37 or 38 on the other side. So you can see a distinct increase in hardness in the weld due to welding. Now, the actual measurements over here are slightly more than 50 because of measurement variations in those regions. And we also see that the base metal hardness is also quite high. And that is possible because some of the hardness will come from previous work hardening processes such as rolling, extrusion, bending, forming, stamping, and so on. So if that hardness is not annealed prior to welding, then the parts themselves can have substantial hardness even before we go into welding. But nonetheless, the maximum hardness is typically governed by the carbon content. So now we're going to go back and look at the TTT diagram once again and look for a strategy to reduce that hardness. And I'm showing you this schematically over here. We can see the step one. Step one is the end of the welding pulse. When the welding pulse ends and the current drops very, very quickly, the copper electrodes tend to provide a lot of cooling, and they can really significantly increase the cooling rate in the weld, and that can cause martensite. Now, once the martensite is formed, we wait for some time to allow the whole process to go through. And then in step 3, we increase the current. We again send a second pulse, which is the tempering pulse, to a level where we heat up the martensite, but not so high that we again transform it back to austenite. Now, how would you know that? Now, that is difficult to measure inside a weld, so you do have to conduct some testing and optimization to find out exactly how much current would you use. But typically, I would recommend starting with about 40% of the welding energy and about twice as long as the welding pulse. So that's a starting point for you to do some experimentation. So the tempering process works by allowing the weld to cool down, wait for some time, and then send a tempering pulse, and which again, then you cool it down. And then you send the samples to the lab to see if there has been a drop in hardness. So when you send that extra energy in the tempering pulse, you allow the martensite to break down into ferrite and cementite. So it allows it to decompose. Now, how much you want to decompose, that's up to you. And that's where the optimization comes in. So we did a tempering cycle on one of the welds and sent it to the lab. And these are the results that we got. So we see that in the as welded condition, the hardness was slightly more than 50, say around, say 52.5. And in the weld zone, after tempering, the hardness has kind of dropped to about 42.5 or 43. So about a 10 HRC drop in hardness in the weld zone. You're also seeing a slight drop in hardness in the regions surrounding the heat-affected zone. So there is some amount of heating even beyond what is a visible heat-affected zone. So here it seems like this is the visible heat-affected zone, but there is going to be some heat dissipation further out. So the true heat-affected zone can be much further out where there is a drop in hardness. Now, that drop in hardness on the edges is more from stress relieving. So whatever the work hardening was there, that has been dissipated because of this heat allows that part to soften. So the mechanism of softening further away from the weld is a little bit different, and mechanism of softening where you see more dramatic drop in hardness is because of the tempering cycle. So in summary, a rapid cooling is very typical in resistant spot welds and likely to result in the maximum hardness due to formation of martensite. Resistance welding, because of the electrodes which are in contact with the part, and often these electrodes are cooled with chilled water. At the end of the weld, the cooling rate in resistance welding is one of the highest in the welding processes, matched only by, in some cases, by laser welding, laser spot welding. So resistance spot welding and laser spot welding have the highest cooling rates in there. So it is very difficult to avoid formation of martensite in resistant spot welds. So if the weld hardness is a bit too much and you want to reduce that, you can send a tempering pulse after the welding pulse. But the beauty of resistance welding is you can actually do the tempering while the parts are still in the machine. So while the parts are still clamped between the electrodes and you have just finished welding, you wait for a short amount of time and send the tempering pulse. All this in the welding machine itself, and that is the uniqueness of resistance welding. So here we do some tempering, and tempering is a heat treatment process that allows martensite to break down into ferrite and cementite. Now keep in mind that you can do tempering in other welds as well, but then you require a secondary source of heating, and that can include either some kind of a torch heating or taking the weld and putting it in a oven to raise it to a tempering cycle. But it doesn't have the convenience of tempering in resistance welding. Of course, the amount of reduction in hardness from tempering can be programmed as required. You can make it less hard or more, or less or more drop in hardness. But keep in mind that resistance welding is the only process where tempering can be performed while the parts are still in the machine as part of the welding cycle itself. So this is a fascinating aspect of resistance welding. So in this video, we have looked at two different aspects. One is the uniqueness of resistance welding and the fact of tempering. Tempering is a process of reducing the hardness in the weld by providing additional heat so that the martensite breaks down to a softer phase. Thank you for your time. And there are other videos in these playlists on different subjects such as resistance welding, laser welding, arc welding, and welding and metallurgy, which you might find informative. And I want to wish you the very best in your efforts to improve your welding quality. Thank you and take care.